Electrostatics, electrostatic devices. This is another lecture where this will be the theory lecture and then some example lectures following this. So we'll have to begin with a derivation of Laplace's equation, and along with that is also something called Poisson's equation. And this really is the analog of the wave equation in electrodynamics. Now there's no waves here, but this is very often the equation that we have to solve to analyze some electrostatic device. So we're going to derive Laplace's equation. I want to discuss a little bit about what it actually means so you have an intuitive feel of what type of answers it gives. Then we'll talk about solving Laplace's equation. From there, we can actually move on to electrostatic devices, which are resistors and capacitors. We'll lay out a recipe to analyze these devices, talk about the devices themselves a little bit, and then in following lectures are the examples where we do the detailed analysis of resistors and capacitors. Derivation of Laplace's equation. We'll start this derivation actually by deriving something that's more general called Poisson's equation. And Poisson's equation is essentially a combination of all of our governing equations for electrostatics. So we have Gauss's law, del dot D equals rho V. But we have the constitutive relation, and so we can replace D with epsilon E to essentially get the divergence equation for the electric field intensity. We also know that the electric field is the negative gradient of the electric potential, and we can replace the electric field with that. And so we're almost there. We're almost at the inhomogeneous Poisson's equation. The last thing we need to do is to take this negative sign outside of the del operator and then move it over to the right-hand side of the equation. When we do that, we end up with Poisson's equation for inhomogeneous media. So what's meant by inhomogeneous? That means the permittivity is changing as a function of position. We have combinations of multiple materials all at once. Well, if the permittivity is a function of position, we cannot bring it to the outside of that del operator. So here it stays, and that's Poisson's equation for inhomogeneous media. Now, what if we're in a homogeneous medium? Well, this permittivity now can come to the outside of the del operator, and then we can bring it over to the right-hand side of the equation. When we do that, we end up with del dot del V. And it turns out this sort of double del operation is written as del squared. And in fact, this is called the Laplacian operation. But we end up with Poisson's equation for homogeneous media. That is where the permittivity is a constant. Now what happens if there's no charge? In this case, Poisson's equation reduces to Laplace's equation. So if we set this charge term to 0 for Poisson's equation for inhomogeneous media, we get Laplace's equation for inhomogeneous media. Let's think back to make some sense out of this. We said nothing can happen in electrostatics without charge. And suddenly we've derived an equation that ignores charge. Well, in fact, it's not ignoring charge. What we'll be doing is we'll be solving this equation in the gap between charges where there is no charge. And at the boundaries, the charge will force some kind of potential. So we're actually solving this equation where there is not charge. There's charge just immediately outside of that. Okay, like we did for Poisson's equation, what if the permittivity is homogeneous? Well, now we can bring it to the outside of the del operator, which means we can bring it over to the right-hand side of the equation, and then 0 times the permittivity is just 0. So the homogeneous Poisson's equation reduces to just what is commonly called Laplace's equation, but that's really Laplace's equation for homogeneous media. And that's really the equation that we use in electrostatics. It's very rare that we would back up to the other ones. And just to remind us, this del squared is called the Laplacian. We're not getting into it now, but there's really two types of Laplacians. We can have a Laplacian operating on a vector function, which gives us another vector function, and we can have the Laplacian operating on a scalar function, which gives us another scalar function. The electric potential is a scalar function, so in this case the Laplacian is giving us another scalar function. So we summarize our equations in this little quad chart. In the top row we have Poisson's equation, which we use when there's charge. In the absence of charge, Poisson's equation reduces to Laplace's equation. In practice, we tend to use Laplace's equation for homogeneous media. We're using these equations because we'll be handed some electrostatic device, we'll assume some kind of charge on that, and we want to figure out what the fields look like around that. Well, the intermediate step is first to calculate the potential, and we're solving this equation to do that. Once we know the potential, then the negative gradient gives us the electric field intensity, and so on. We're also using these equations because we could go back to Maxwell's equations, but those are vector equations, and those are just harder to solve. We prefer solving scalar equations. If there is charge where we're obtaining a solution, we resort to Poisson's equation, but that tends to be very rare. Laplace's equation, in practice, we are solving Laplace's equation in homogeneous media. So this is a very, very important equation because it allows us to pretty easily figure out the fields around charges and metal structures. And last, and unfortunately, we just can't spend a lot of time on this, but there is something called the uniqueness theorem, which is very important. And this says if we find a solution, it is the solution. There is only one solution. So even if we took a wild guess and plugged that guess into this equation and found out that it's a valid answer, that is the answer. There are no other answers. There's only one answer to this. And that comes from the uniqueness theorem. I want to take a detour from the hardcore electromagnetics and try to give you a very intuitive feel of really what Laplace's equation is doing. So put aside the electromagnetics. Let's just think in terms of math and numbers and how we can fill in numbers where there's missing information. So here's Laplace's equation, and just to think like a mathematician, I'm using U instead of V. So we have Laplace's equation for homogeneous media. So the del squared operator, that's really a three-dimensional second-order derivative. So what do we know about second-order derivatives? Second-order derivatives are somehow quantifying curvature. Now in 3 dimensions, curvature is a little bit more involved than the Laplacian. It involves Hessians and other things, well, we don't need to get into. But it still, in some way, quantifies curvature. If there is no curvature, then the second order derivative will be 0. Well, we're saying the second order derivative of u is 0. So what that's really saying is that the solutions to this have to form straight lines. They have to be linear because the second order derivatives are 0. So that's our first hint about really what this Laplace's equation is doing for us. So we set up a problem here, and I'm drawing this array looking thing because we have to do this numerically. There's probably not an analytical solution here. But let's say we have a metal object here that we set to -9 volts, and another metal object out here that we set to +9 volts. The question is, what is the voltage in between? This is something we need to know to analyze electrostatic devices. So that's what we're asking. In the white space here, what does it look like? How do we get an answer to that question? And that's really where Laplace's equation comes in. We solve Laplace's equation in the white region. And we're using these known potentials, the -9 and the +9, essentially as boundary conditions. And Laplace's equation fills in all of the other numbers. So if we obtain that solution, boom, there's all the other numbers. And every number here is varying as linearly as possible from the -9s to the +9s. So we can pick a number here, and what Laplace's equation sort of was doing was looking at this metal object and this metal object, looking at the distance between the two and figuring out what number it should be such that it would vary linearly. And what we've done here is calculate the potential between these two metal objects by solving Laplace's equation. So in that sense, Laplace's equation is sort of like a number filler-inner. But it's important to know that these numbers are grading linearly across our space that we've solved it. Here's another example where maybe we have a completely bounded problem. We might know the values all the way around the perimeter. And we don't care what's going on the outside, but we want to know what the numbers are in the middle, such that they vary linearly. So again, we ask Laplace's equation, what's the answer to this? And out pops all of those numbers in the middle, such that they vary linearly. Okay, let's talk about solving Laplace's equation analytically now. So Laplace's equation is solved as a boundary value problem. That means that the del squared V equals 0 is not enough to obtain a solution. If that's all we're given, then we'd have to write that the potential is just 0 everywhere, or some background reference potential. But we need boundary conditions. We need to know what the potential is at least one other point to solve. So here's the recipe. We'll choose a coordinate system. So if your device looks like a cylinder, we'll choose cylindrical coordinates. If it looks like a block, we'll choose Cartesian coordinates. This should be pretty much habit by now. Then we go ahead and actually solve Laplace's equation for every homogeneous region in your device. Hopefully this is only one, but if there's multiple, then you have to solve Laplace's equation multiple times. Now, for one-dimensional problems, we can actually solve Laplace's equation by direct integration. If not, then we have to use separation of variables, and the math is a little bit more complicated. But we'll go through all this when we get to the examples. Once we have the general solution, we'll have constants in there, and we apply the boundary conditions at the edges of our homogeneous regions. Once we know the potential, we've essentially solved our problem. From there, we calculate E from the negative gradient of V. Then we have the electric field intensity. Then we can calculate D from E. So we have the electric flux density, and we really know everything about the problem at that point. Okay, let's apply this to a simple problem. So here's the setup. Let's say we have some medium with some permittivity epsilon, and we put two conductive plates on either side, and we separate them by a distance d. So the bottom plate will be located at position 0, and the top plate at position d. Then we apply a voltage. Call that voltage V0. That V0 will put charges on the plates. So our job, given all this, is to calculate the electric potential and the electric field between the plates. So just in the region between the plates. That's our problem. Let's use the recipe that we just outlined to solve this. So step one, choose a coordinate system. Well, in this case, my device looks rather blocky, so I like Cartesian coordinates. And in fact, it's only a one-dimensional problem here. So Cartesian coordinates will work for us. Step two, now we solve Laplace's equation. Since this is a one-dimensional problem, ultimately we'll be able to solve this by direct integration. So we start off by writing Laplace's equation and our boundary conditions. At this point, we could take this set of equations and hand it off to a mathematician who doesn't even really know what we're solving and be able to give us an answer. So from this point forward, we're mathematicians. The first thing I like to do is expand this into Cartesian coordinates, in this case, because we're using Cartesian coordinates. And since we're only caring really about between the plates and not really what's happening at the edges with the fringing fields, it reduces to a one-dimensional problem. And why am I choosing to ignore the fringing fields? Because that way overcomplicates the problem, and in my opinion, that's best done numerically, not analytically. So we're obtaining a solution in the middle of these plates, in between them. So based on that, we only care about this z or vertical direction. So we can just set the other derivatives to 0. And really what that's saying is we're analyzing a capacitor that's essentially of infinite extent in the x and y directions. When we do that, we only have one independent variable left, z. So our partial derivative is reduced to an ordinary derivative, and that's why we can use direct integration. So we now have a one-dimensional problem here that we have to solve, and over here are our boundary values that will let us find the constants that we get when we solve this differential equation. Onward to the solution. So if we integrate this twice, we get the equation essentially of a straight line. So it's some linear function of z, and that makes sense because our potential should be varying linearly, but we have these constants a and b that we do not know, and this is where we'll apply those boundary conditions to figure those out. So at our first boundary, at the bottom plate, the potential is 0, voltage is 0. So voltage at the bottom plate equals 0. I plug in 0 for z, and I get a times 0 equals b. So the a disappears for right now, and we just end up with b equals 0. So that constant b is 0, and the boundary condition at the bottom plate told us that. We have a boundary condition at the top plate. The voltage at z equals d at the top plate is v naught, our applied voltage. So v at d is a times distance d, because that's our value of z, and we now know that b equals 0. So now we have a times d equals v naught, and we can solve that for a, and a is v naught over d. Now that we know a and b are constants, we can plug them back into our original expression for the potential between the plates. And that's exactly what we do, and this is our answer. So the voltage as a function of position between the plates is v naught over d times z, and this is to remind us that that solution is really only valid from 0 to d. We haven't solved this outside of the capacitor. That's really where we would have these fringing fields. It looks really cool, but it's very, very difficult to do, and in my opinion, best done numerically, not analytically on paper. Well, we have our answer. Now we're at step 4. We want to calculate the electric field. The electric field is a negative gradient of the potential. So now we have an expression for V. We know we're in one dimension, so we plug in our expression for V. We take the derivative, and we just end up with negative V naught over D. And this is a constant, which is what we are expecting the electric field to be. We're expecting it to be a constant. It is uniform between those plates. And so that's only the z component, so we can write the electric field as a vector, and the negative sign is indicating that the electric field is pointing down. And that makes sense because the electric field emerges from positive charges, which would be at the top plate, and then ends on negative charges. So now we have the electric field E. And if we want the electric field, or the electric flux density D, we just apply the constitutive relation and we multiply by the permittivity. So here's our electric flux density D. And it looks the same, just scaled by a constant, the permittivity. Okay, on to resistors and then capacitors, and this discussion will be relatively short because the majority of this work is reserved for the examples. But let's talk about resistors and lay out how we're going to analyze them. So a resistor, it's a two-terminal device. It's a passive device. Hopefully you've taken circuit theory, so what a resistor is should be pretty simple. It opposes current. It is partially conductive. We might even put this in the semiconductor category that we talked about earlier. It's not a switchable thing. You know, we could have tunable resistors, but it is resistive, partially conductive, and lots of different things. We have a power resistor here. We have schematic symbols for resistors, various forms of resistors. We have our color code for resistors. We have surface mount chip resistors, and lots more that I'm not showing here. So let's say we want to analyze this, and here I'm showing some kind of volumetric thick thing that is partially conductive. And the overall length of this is L. It has conductivity sigma. And if I look at the cross-sectional area, which is arbitrary, we'll just call that area S. Then we apply a voltage V to it, and based on its resistance, it will allow some current to pass through that. Well, we define the resistance of the device as voltage divided by current, and we want to know what that is. Let's look at a case where we have a uniform conductivity and derive our expression for resistance. So we start with Ohm's law that says the current density J is the conductivity times the applied electric field. So the electric field is extending from one face to the other, so from the positive face to the negative face, and that gives us some current density here. Well, we just derived really that the electric field intensity inside this medium is the applied voltage over the length of it. Well, what is the current density? It's the total current divided by the cross-sectional area. But we also said that the current density is sigma times E. So we can put that there. Well, we also now have an expression for E. It's V over L. So we can replace E here with V over L. So now we have IS, I divided by S, equals sigma times V over L. That's our new equation. But now we have an equation with V and I in it. So we can arrange this equation until we get V divided by I, and we see what that equals. So V divided by I is L over sigma S. Well, V divided by I was our definition of resistance. So we've actually derived our resistance when we have a uniform conductivity. And so there's our final answer. Resistance is the length of the resistor divided by the cross-sectional area and also divided by the conductivity. Now, sometimes we're not given conductivity, we're given resistivity, which is just the inverse of conductivity. So that's how we get the resistance of a structure that has a uniform conductivity. Now, what happens if it's a non-uniform conductivity? Now we have to resort to some electromagnetics to figure out what V and I are. So the voltage across the conductor, once we know what the electric field is, we can do a line integration to calculate what the voltage is across the resistor, given the field. We need to know the current through the conductor, and there's two ways we can do that. We can integrate the current density. We can also integrate sigma times E, right? That's J, that's our current density, and that will also give us the total I. Once we have these two expressions, we can divide the two, and we have resistance. So I can very roughly write this equation, and that really spells out the recipe that we would have for deriving the resistance of an arbitrary structure where we have to resort to these electromagnetic equations. Okay, so here's our recipe that we will use to analyze resistors. So, like always, we pick a coordinate system. For us, we will assume a V0. We will assume an applied potential. After that, we'll calculate the potential everywhere else by solving Laplace's equation. And in practice, this is finding the voltage between the plates or the metal objects. Once we have that, then we calculate E as the negative gradient of V. Also, knowing E and the conductivity, we can calculate the total current. And then once we have the voltage, which we've assumed, and the current, which we've just found, we divide the two to get resistance. Now, a great check to know if you're right is that the overall resistance should no longer be a function of voltage. So if your final expression for resistance contains anything about current or voltage, chances are we're wrong. It really should just have to do with the conductivity and dimensions of the device. So use that as a self-check. So this is as far as we're going to take resistors here, but there's a bunch of examples following to practice what we're teaching here. We'll end our discussion of resistors with this. So we have a parallel plate resistor. Kind of looks like a parallel plate capacitor. It is, but now we're talking about a medium that is partially conductive. And in a following example, we derive the resistance of this using our electromagnetic equations. And so it's just the separation of the plates divided by conductivity and also divided by the cross-sectional area of that resistor. On to capacitors. Like resistors, capacitors are two-terminal devices. They store and release electric energy, and they act in a way that tries to keep the voltage across their terminals constant. And they can, for a short amount of time anyway, supply huge amounts of current to try to keep the potential across their plates constant. And in fact, in the older days, before cameras were using LEDs, they were using flash lamps. Internally in the camera, they would charge a bank of capacitors and discharge them so it could supply this huge burst of current to the lamp. The lamp didn't take a high voltage, but it needed high current. And in fact, you could even hear your camera charging, and you could only take pictures so quickly because it would have to charge the bank of capacitors back up. That's not really a problem today. So capacitance is a device that stores charge. So if we apply a voltage to it, it will get charges on the plates. And if we have a large capacitor, we'll get more charge for a given voltage. And so in fact, capacitance is defined as the ratio of how much charge is accumulated for some applied voltage. Now notice I'm having the absolute value here because when we do analysis, sometimes we might have the voltage going the other way or whatever. And so the signs don't matter here. We can't have negative capacitance. So capacitance is Q over the applied voltage. So here's our recipe for analyzing capacitors. So we'll be handed some twisted tangle knot of metal, and we'll have to figure out what is the capacitance of that structure. So number one, choose a convenient coordinate system. If it looks like a cylinder, pick cylindrical coordinates. It looks like a block, pick Cartesian. The next thing we'll do is let the plates carry a charge plus Q on the positive voltage plate and minus Q on the negative voltage plate. So they're carrying the same charge, just opposite sign. So that's assumed. Once we have charge on the plates, we can go back to earlier lectures where we talked about fields around charges, and we can figure out what the field looks like around those charges using Gauss's law. This is also where we'll borrow what the field looks like around the infinite plates and infinite wires, because if this is what the elements in our capacitor look like, we can jump much more quickly to a good estimate of what the field looks like. So we'll use that a lot. So anyway, we use Gauss's law, we get the D field around these charges. Once we have the D field, well then we have the E field just by dividing by the permittivity. That comes from the constitutive relation. Once the electric field intensity is known, then we can calculate the voltage between the plates by doing a line integral from plate to plate. Now we have the charge and the voltage. We're now in a position to calculate capacitance, and we'll ignore the signs here because capacitance is always positive. So we get some tangled piece of metal, we assume a charge, calculate the fields around that, do a line integral from plate to plate to get the voltage, and then charge over voltage is our capacitance. Unfortunately, we're not going to exercise that recipe in this lecture. That will come in some following examples. And the results, the two important results from those examples, one, we analyze a parallel plate capacitor. This is a classic analysis. And the capacitance of this parallel plate is the permittivity times the cross-sectional area divided by the plate spacing. We also go on to analyze the capacitance of a coax, where we have a center conductor, we have an outer conductor, some kind of dielectric fill, and that coax is some distance L long. And we arrive at a nice, pretty clean expression for the capacitance of that structure. So here we're exercising Cartesian and then cylindrical coordinates. So that's it for this lecture.